A conformation is an exact arrangement of atoms in a molecule. Not just how they're attached, but how they relate to each other in space. You know that the bond line convention for drawing organic molecules is quick, easy, and effective. It shows a lot about structures. It even lets us show 3 dimensions. Take a look. Here's the structure for butane, and if we want to show 3 dimensions, we can use wedges and dashes. So the wedge tells us a hydrogen is coming out toward us, and the dash tells us a hydrogen is going back. We could do the same thing for the next carbon. This structure is useful and accurate, but it's not real easy to see the relationship between substituents on one carbon and the atoms attached on the next carbon. So there are other conventions that work better for showing the exact spatial arrangements, which we call conformations. Let me show you. Suppose we cite placing our eye here and looking straight down the C2-C3 bond of butane. So we're looking there. We're looking at this atom, along that bond, and at this atom. There's a sawhorse convention that lets us show this better. We'll draw the 2 carbons, as shown in butane to the left, and then let's draw in the atoms attached to it. When we're looking at this one that is closest to the eye, we see a methyl group that looks like it's sticking straight up if we're looking along that bond. So we'll put it here. And that leaves hydrogens, as shown. And in the back carbon, you can see that methyl group is sticking down. So in the sawhorse representation, it's right here, sticking straight down. And that leaves 2 hydrogens. Using this convention, it's easier to see the relationship between any 2 atoms on this carbon and any 2 atoms on this carbon. For instance, it's so easy to see that the methyl group sticks straight up on one and straight down on the other. But with respect to specific angles that exist between these other atoms on one carbon and the other are still not real easy to see. So there's another convention called the Newman projection that's even better. Again, we position our eye so we sight down along that C2-C3 bond. The carbon that our eye sees first, I'm going to mark with a brown dot, and the center of that carbon in the Newman projection is depicted like this. And now again, we see that there's a methyl group sticking straight up, and that carbon has hydrogens down and to the right and down and to the left. And the back carbon, which we can't see with our eye because it's hidden by the first one, has substituents represented by sticking out from behind. And straight down, again, there's a methyl group, and the hydrogens are up to the right and up to the left. And the advantage of the Newman projection is it now lets us see very clearly the spatial relationships, including angle, of a substituent on one carbon and the substituent on another carbon. So whichever ones we pick, we can easily see what their spatial relationship is. And for that reason, this Newman projection is the convention that's most useful when we're trying to understand conformations of acyclic compounds. So we'll use the bond line with wedge and dash when we don't care too much about determining those angles and looking at them exactly. But we'll switch over to the Newman projection when we want to see the actual relationships between atoms on one carbon and on an adjacent carbon, including looking at the angles themselves.